Hello and welcome to Empowered Learning. This particular video is the fourth video in the Radical Expression series. In this particular video, we will talk about adding, subtracting, and multiplying radical expressions. So we want to first start out by distinguishing what we mean by a like radical expression versus an unlike radical expression. And so the way that we're going to deal with these expressions as far as adding and subtracting them together at least is we're going to treat everything that has like radicals kind of the same way as we do when we deal with polynomials and we have terms that are what we consider like terms. And so we'll combine those together. All the ones that are unlike, we will not combine those together. And so to get an idea of this, the first thing that we want to recall is that the square root of any prime number is an irrational number, okay? Sort of like square root of 2, square root of 3, square root of 5, square root of 7, those numbers, okay? They're irrational because those types of numbers cannot be written in terms of a fraction. In other words, they cannot be written as a terminating or repeating decimal, okay? So the best that we could possibly do with those is to do a decimal approximation like I have shown here in this example. But the main thing that we want to look here is that any expression that has square root of 2 in it will be an unlike radical expression in terms of anything with square root of 3 in it, okay? And so my point here is that if we look at the expression square root of 2 plus or minus square root of 3 here, or put another way, square root of 3 plus or minus square root of 2, if we look at it commutatively, then we see that we're not going to be able to really add those numbers together to get an exact answer. So we would just leave the expression as square root of 3 plus square root of 2 here, or if we're subtracting them, square root of 3 minus square root of 2. And so we consider square root of 3 and square root of 2 to be what we call unlike radical terms, okay? Now, if we have a like radical term, then we're going to see some of the same type of square roots in them. So for instance, in our first example here, we see we have 2 times square root of 3 plus 4 times square root of 3 minus square root of 2. The 2 times square root of 3 and the 4 times square root of 3 are what we call like radicals because they both have square root of 3 in it. And so we're treating it the same way as if this sort of said 2 times x plus 4 times x minus y. That's sort of how we're doing it. If we had this and we were dealing with polynomials, we would say that this is 6x minus y. In the same way, we're treating this first example here where we'll combine the 2 times square root of 3 and the 4 times square root of 3 to be 6 times square root of 3. And of course, the square root of 2 is an unlike term, so it's by itself. And so here there should be a square root on that. Okay. Similarly, we see that negative 3 times square root of 5 and negative 7 times square root of 5 combine together to be a negative 10 times square root of 5. And we see that 4 times square root of 2 is by itself. So that's probably one of the main things we need to remember whenever we're dealing with radical expressions that we have to add or subtract, that we treat anything that has like radicals in it together. Anything that's unlike, we keep them separate, okay? So some key points to remember here is that if we have a number expression in the nth root form where a is some prime expression, then we know that that particular radical expression is already in its simplest form, okay? Can't be broken down anymore. So that's kind of like how we're saying with square root of 7, can't be broken down anymore. Like radicals, I mean, I'm giving you the formal definition here, are radicals that have the same index and the same radicand, okay? So like how we saw, I'll just make up new example, 4 times square root of 3 plus 2 times square root of 3. The index is the same. So for this example, the index is 2, and the radicands, or the expression under the radical, is the same. That is 3. Okay. If we don't have a situation where both the indices and the radicand are the same, then we consider the radical terms to be unlike. Okay. And so we want to remember only radicals with the same index and same radicand can be viewed as like terms, thus combined when doing addition and subtraction. Okay. Now, whenever we multiply radical expressions, we can multiply them as long as they have the same index. Okay. Meaning if I take square root of 2 and I want to multiply that times square root of 6, I can combine that to be square root of 12. However, if I had cube root of 2 times square root of 6, I cannot multiply these together just yet. Okay. So if two radical expressions have different indices, but the same radicand, then we could do multiplication. But we would have to change it into its fractional exponent form first before we do that. And so we'll see some examples with that. To give you a, I guess, basic example of what it means to have two radical expressions that have different indices but same radicand, let's say we have cube root of 3, and then we want to multiply that times, let's say, square root of 3. Okay. In that instance, what we're saying here, in order to try to multiply and combine this together, I would have to essentially change cube root of 3 as 3 raised to the 1/3, and then take square root of 3 and change it as 3 raised to the 1/2, and then use my exponential properties to basically say, hey, this is the same as 3 raised to the 1/3 plus 1/2. And then, of course, with the fractional exponents, I will have to find a common denominator in between both fractions, and then form equivalent fractions, and then from that add them together, and then change it back into radical form. Okay, and so again, we'll see plenty of these examples a little later. Just kind of want to give you some quickies as far as knowing what we're talking about here. Okay, here's another example. If we have the fifth root of 3 times the cube root of 3, notice how we take this and we put it into its fractional exponent form. We know from exponential rules we can add the exponents if we have the bases are the same. We form an equivalent fraction, and then after we get that, we get a single exponential, an equivalent single exponential form of the product, and then after that we write it back in radical form. Okay. Another thing that we want to touch on is conjugates, and so we recall that a minus b times a plus b from whenever we deal with polynomials, and in particular quadratics, is going to be a squared minus b squared. Okay, so if we have two irrational expressions of the form a minus b and a plus b, then we know that we can simply multiply these two expressions together by squaring what is a, squaring what is b, and then taking the difference of it. Okay, so in our first example here, we see that we have 3 plus square root of 2 times 3 minus square root of 2. Both of these expressions are irrational, and they are conjugates because they only differ by the binary operation of addition or subtraction. And so from that, we consider a to be 3, we consider square root of 2 to be b, so we just say a squared minus b squared, okay? Where our a is considered to be 3 and our b is considered to be square root of 2. So if we work that out, we see that we get 7 in this example. In the next example, we see that a here is considered to be square root of 3x, and our b is considered to be square root of y. And so, of course, whenever we work that all out, we would say that this ends up being 3x here. And of course, if we were doing this and didn't know what x actually was, we would probably put the absolute value signs on the x part. Okay. All right, so we're going to go ahead and start working some examples now so that we can get the hang of what's going on here. All right, so we want to simplify sum by using the sum of difference formula to give an expression. All variables assumed represent positive numbers. Okay, so in other words, if we see an a or a b or x or a y, all those are considered to be greater than 0. So that means that whenever we see the situation of having square root of x squared, we can just write it as x instead of as absolute value of x. Okay, so that's the main reason why that particular expression is important. All right, so let's go ahead and get rid of all of this and get started. So we see in example B here that we have like radical expressions here because we have square roots. Our indices, well, our index for both of these is 2, and the radicand is the same. So we treat this like if it was 5x plus 4x, and of course we would say that that's 9x. So here, looking at it this way, we would say that this would be 5 plus 4 times square root of 7x, which would just be 9 times square root of 7x. Okay. I did skip example A, but it's sort of the same thing. We have an understood 1 times square root of 3 here minus 2 times square root of 3. And so you see that they are like radical expressions. So we just say 2 minus 1, which is a negative 1 times square root of 3. Okay. Similarly here, we have an index of 3 that's the same. The radicand is 2 that's the same. So we just add these together, and this will be 5 times cube root of 2. Okay. For example D, we have square root of 6a in both. So we just subtract. Okay. So we have 3 minus 7, which is a negative 4. So that'll be negative 4 times square root of 6a. Now for our next example here, notice that we have like term here, and then these are like terms. So have an understood 1 there, so 1 minus 7 is a negative 6, and then times square root of 2, and then we have negative 5 plus 9, which is a positive 4 times square root of 3. That would be the answer for that. Similarly, for example F, we see that cube root of 5y minus 4 times cube root of 5y. These are two like terms, understood 1 right here. And these are two like terms, understood 1 right there as well. So we say 1 minus 4, which ends up being a negative 3 cube root of 5y. And we say 1 plus 4, which is equal to 5 times cube root of x. And so for example G, we see that we have cube root of AB, like term, like term, like term, like term. Okay, so we got understood 1s here. So 1 plus 1 is 2 cube root of AB. And then we have understood 1 there. So let's try to write that 1 a little better. Understood 1 there. So 1 plus 5 is 6 times square root of 8. And that's what that expression would simplify to. Okay. All right, so our next set of examples, we have to do a little bit more work here. So for this, we see that square root of 12 and square root of 24 are definitely not the same. But if we rewrite the way that it looks to break each term down into its simplest terms, then we'll hopefully find something that is alike with it. So we know that square root of 12 can be rewritten as square root of 4 times square root of 3. And we also see here that square root of 24, we could rewrite that as square root of 4 times square root of 6. We could do it like that. We know that square root of 4 is just 2. And so this would just be 2 times square root of 3 plus 2 times, but square root of 6 could be rewritten as square root of 3 times square root of 2. Okay? So we see we do have like radical expressions in that both of these have square root of 3. So here, if we were to combine this together, we would say that this would be 2 plus 2 times square root of 2, all that times square root of 3. So it'll look like this: 2 times 2 square root of 2, all of that times square root of 3. And that would be the simplified form for example A. For example B, you see that we're doing pretty much the same thing. We write down square root of 20 as square root of 4 times square root of 5. Break down square root of 125 as square root of 5 times 5 times 5. And of course, if we break that down some more, we see that it just looks like square root of 25 times square root of 5. And so from there, we know that square root of 25, which I have written here as square root of 5 times 5, is just 5. So that's where this 5 comes from. The square root of 4 is 2, so that's where we get that from. And we see that in both terms, we have left a square root of 5. So we know that these are like terms. So 2 minus 5 is a negative 3. And then we just append on the square root of 5. All right. So for example C, we're going to do the same thing. We know that 50 is 25 times 2. So we could look at this as 3 times square root of 25 times square root of 2 minus 2 times 32 is 16 times 2. So that would be square root of 16 times square root of 2. We know that square root of 25 is 5. Square root of 16 is 4. So we have essentially 3 times 5, which is 15 times square root of 2, minus 2 times 4, which is 8 times square root of 2. And of course, 15 minus 8 is just 7, and append the square root of 2. Moving on to the next example, you see that this one is a little bit involved, but concept is the same. So we take square root of 12x raised to the fifth, and you can see here we break down square root of 12 as square root of 4 times square root of 3. We break down square root of x to the fifth as square root of x squared times x. And so from there, just working on that term, we know that square root of 4 is 2, square root of 3 stays by itself. Since we have square root of x squared, for every 2 factors of x we see, we pull 1 out. So we have 1, 2 there, and have a square root of x left. And then, of course, this simplifies to 2x squared times square root of 3x. So everything that's on the outside multiply together, everything that's on the inside of the square root we do together. So from this point, we deal with our second term, square root of 18x, which is square root of 9 times square root of 2x. And of course, square root of 9 is 3, so that's how we get that. And that remains the same there. Square root of 300x raised to the fifth. We see that Square root of 300 could be broken down to square root of 100 times square root of 3. And of course, square root of 100 is 10. Square root of 3, leave that alone. And just like how we saw here, the square root of x to the fifth just ends up being x squared times square root of x. Okay. And so of course, if we bring all that together here for the third term, we end up getting 10 times x squared, and then on the under the square root sign, square root of 3 times x. And of course, for the last term here, we break down square root of 98x as square root of 98 times square root of x. And square root of 98, since we know that 49 times 2 is 98, this breaks down to square root of 2 times square root of 49. And of course, square root of 2 can't be broken down anymore, but square root of 49 can, and that's 7. And of course, since the 2 and the x are both under the radical, we have square root of 2x there. Everything that's on the outside, which is just 7, is here. Okay? And so now that's how we end up with 7 times square root of 2x. So of course, if we look from this point here, we see that we have like terms. This first term here and this third term are like terms. The second term and the fourth term are like terms. Okay, so I'll just go ahead and do the little symbol coding that I've been doing before. So this is like term, like term, like term, like term. And so here we have 2x squared minus 10x squared gives us a negative 8x squared, square root of 3x. And then we have a negative 3 plus a positive 7, which is a positive 4 times square root of 2x. So I know that one was a little more involved, but as you see, if you take it step by step, they're pretty easy to do. All right, so moving on here, we'll work on this next example, E. We see that we have 5 times, and we know 24 could be written as cube root of 8 times, was cube root of 24 could be rewritten as cube root of 8 times cube root of 3 minus. Here we have 2 times 375. 375 is 125 times 3. So we could rewrite this as cube root of 125 times cube root of 3. Okay. And of course, cube root of 8, which is the number that we have to multiply times itself 3 times to get 8, is 2. And cube root of 125 is just 5. So this ends up just being 5 times 2, which is 10, times cube root of 3 minus 2 times 5, which is 10, cube root of 3. And we see that that's the same thing, so our answer just ends up equaling 0. Okay. All right, and so for example F, that one's sort of involved like this last example D here. I won't go into great detail about that. I'll just pause for a second so that you can actually see everything worked out, and everything should work out fine once you take a look at it. So I'll pause for about 10 seconds to let you look at it, and then I'll move on to the next set of examples. Okay, so let's go ahead and move on. So now with the next set of examples here, what we want to do is we want to simplify the following products. Okay, so here we see that square root of 5, square root of 7, we can multiply these together, but this is about all that we can do. Okay, for example B here, we're going to multiply everything that is on the outside together, so that will be negative 12. Multiply everything that's on the inside, and that will be 2 times square root of 10, which is 20, okay? And of course, 20 can be broken, square root of 20 can be broken down to square root of 4 times square root of 5. We know that square root of 4 is just 2. So negative 12 times 2 is a negative 24. And then we append the square root of 5 at the end. Similarly, for example C, we see that we have the fourth root of 9 times the fourth root of 27. So we know that we can multiply all that together. We see that in this example that 9 is 3 times 3, and 27 is 3 times 3 times 3. So if you notice, we actually have 4 3's that are factors here. 1, 2, 3, 4. So for every 4 that we see here, we could pull one out. The way that I addressed that and how I wrote it here is to say, let's rewrite all this as the fourth root of 3 to the 4th times 3, and then separate it. And so here's where for every 4 of these we see, we pull one out, and we just have left fourth root of 3. And so that's essentially what I'm doing here, okay? And that 4 doesn't look so hot there, but essentially it just looks like that. For our next example, we have 2 times square root of 3, all that raised to the second power, or it's squared. So we can use our exponential rules and just square each of these. So 2 squared is 4. We know that the square root of 3 squared is just 3. So the answer to that is 12. If we move on here to example E, we'll see that since both these are under square root, we can multiply all this together. So we have square root of, and I'll just keep this as 5 times 8 times x to the 7th. I'll just do it like that. We see here that have square root of 5. We know 8 could be the same as square root of 4 times square root of 2. And x to the 7th, if we square root that, that would be, we have x squared and another x squared and another x squared, and then just x, okay? And of course, square root of 4 is just 2. So on the, we know that we're going to have 2 times square root of 10 here, but then we need to figure out how we're going to deal with the square root of x to the 7th written this way. So for every 2 x's that we see, we're going to take one out. So if we were to separate how this is written, and I'll just go ahead and separate all this and rewrite it, we could do this as square root of x squared, square root of x squared, square root of x squared times square root of x. And so for each one of these, it would just be x. So on the outside of the radical, we have 2 times x times x times x, which is 2x cubed. And on the inside, we have 5, 2, and x. And that would just end up being 10x once we do all of that. So final answer to E would just be 2x cubed times square root of 10x. Okay. Now, for the next example here, we see that we're going to be using the quotient rule. And so if we look, we have cube root of a to the 4th divided by 2 times cube root of a cubed divided by 4. And of course, since they both have the same index, we can combine everything together under the radical. So we do that, and we see we have a to the fourth times a cubed, which we could write as a raised to the seventh, but choose to write it this way because we need to have factors in groups of 3 to be able to factor 1 out. Okay. So same thing in the denominator. We know that 2 times 4 is 8, but we could just rewrite it this way. And so by doing that, we know that cube root of 2 raised to the third power is just 2, because that's the same as saying 2 raised to the 3 over 3 power, which is just 2 raised to the 1, which is just 2. Okay, so that's just quick explanation for that. But our denominator just ends up being 2. Our numerator, if we take everything shown here and break it up, we have the cube root of a cubed is just a. Another cube root of a cubed is a. And then we just have a cube root of a all by itself. So we have 2 a's that are outside of the radical. So a times a is a squared. So that's where this comes from. The cube root of a is left, so that's where that comes from. And of course, our denominator, the cube root of 8, is just 2. All right. So moving right along, we see our next 2 examples here. We're doing some multiplying. So here we're using the distributive property. And so in doing that, we see that we could take the first term, multiply it, and we get 2 times square root of 5 times 3, which gives us 2 times square root of 15. And we see that we have 2 times square root of 5 times 3 times square root of 5. And of course, we know that square root of 5 times square root of 5 would be the same as saying square root of 25, which would just be 5. So let me rewrite that again. And so I chose to write it this way just to come up with the answer of 5. So we see simplifying all this is just 5. So 6 times 5 is 30, and we just keep the 2 times square root of 15. Okay. In example H, notice that this is not a situation where we have a conjugate. Okay. In order for us to have a conjugate, this would have to read something like this. Okay. But notice that this 5 and that 2 are different, so that's why we don't have the conjugate case here. Okay. So here we just need to multiply this as normal. And what we mean by normal is we need to multiply this by the FOIL method. So we take first 2 terms, multiply them together. Then we do the outside terms. So square root of 3 times a negative 5. Inside terms, 2 times square root of 3. And then the last terms, 2 times a negative 5. Okay. For those of you that multiply these using either the vertical stack method or the box method, you could do it that way as well. Okay. So once we're here, we see that the 2 middle terms are like terms, so we combine those together to get a negative 3 times square root of 3. The 2 outer terms are like terms because they don't have any radicals in it. We know that square root of 3 squared is just 3, and so 3 minus 10 is a negative 7. Okay, so this is what we end up with as our answer. Now, for our next example, notice that we have the same thing here. Okay, we have square root of 2 times 5 times square root of 2 times 5. So we could do the same thing, multiply using the FOIL method, or we could use a shortcut here. For clarity purposes, I'm just going to do the FOIL method. So we'll just have square root of 2 squared, first terms, then outer terms, then inner terms, and then our last terms. So 5 times 5 is 25. These 2 terms are alike, so 5 plus 5 is 10. So we know that the middle term here will be 10 square root of 2. Square root of 2 squared is just 2. So we see that 2 times 25 would be 27, and 5 square root of 2 plus 5 square root of 2 would be 10 times square root of 2. And that will be our final answer there. For J, we're going to do the same thing. We'll go ahead and let me just move this answer here right quick. So for J, we're going to go ahead and multiply again by using the FOIL method. So here we'll multiply first terms together. So that's 2 times square root of 3 squared. Okay. Multiply outer terms together. So that's 2 times 2, which is 4. And then 3 times square root of 3 times square root of 6 is square root of 18. Okay. And then the inner terms would be square root of 6 times square root of 3. And since that's a negative times a positive, that would be negative square root of 18. And then the last terms here would be a negative 2 square root of 6 squared. Okay? And so for here, we see that square root of 3 squared is just 3. And square root of 6 squared is just 6. So have that. We can combine 4 times square root of 18 minus 1 times square root of 18 to be 3 times square root of 18. So all of this would just be 3 times square root of 18. So if we simplify this, this would be 2 times 3, which is 6, plus 4 square root of 18 minus 1 times square root of 18 would just be 3 times square root of 18, and then minus 2 times 6 would be 12. Okay, so from here we know that 6 minus 12 is a minus 6 plus 3, and now the square root of 18 can be broken down to square root of 9 times square root of 2. We know that square root of 9 is just 3. And so that would end up just being negative 6 plus 3 times 3, which is 9 square root of 2. So this would be our final answer there. For example K, notice that these are conjugates. So here we could take the shortcut route by letting A equal 7, B equal square root of 3, and just using the formula A squared minus B squared. So that will be 7 squared minus square root of 3 squared. And so 7 squared is 49. Square root of 3 squared is just 3. So we just end up with 46 as our answer. Similarly, for example L, we view A as 2 times square root of 5, B as 1. So this would be 2 times square root of 5 quantity squared minus 1 squared. And if we look here, we know that 2 times square root of 5 squared is just 2 squared times square root of 5 squared minus 1. Square root of 5 squared is just 5. And we know that 2 squared is just 4. So 4 times 5 is 20. Minus our 1. Answer is 19. Okay. And so now moving on to example M, we see that when we multiply these together, of course, we see that these are conjugates of one another. So we just say 5 squared minus 3 square root of x squared. And of course, for our second one here, we notice that we can break this up as 3 squared times square root of x squared. And here, notice that the square root of x squared, I put the absolute value of x here, but since we know that x has to be greater than 0 for these problems, we know that absolute value of x will just reduce to just x. Okay. All right, so for example, n, we see that we have radicals, but we're also dealing with fractions. And so it's important for us to follow the rules of fractions, which means we can only add them or subtract them together whenever we have like denominators. So what that means for us, we need to find the LCD. And of course, the LCD for 4 and 5 would be 20. So that means I would need to multiply both numerator and denominator by 5 for the first fraction, multiply numerator and denominator by 4 for the second one. And so now that would give us 5 times square root of 2 plus 4 times square root of 3 all over 20. Okay? And since 5 times square root of 2 and 4 times square root of 3 are unlike radicals, this would be the simplest form. Okay? Moving on to example O, we see that we have 5 times square root of x minus 3 quantity squared. And so what I've done here is, instead of doing the FOIL method, which I could do if I wrote this out to be like this. Let's try that again. 5 times square root of x minus 3 times 5 times square root of x minus 3. If I was to do the FOIL method, I would eventually get what I'm showing you here. The formula that I actually used here is the same one that whenever we say a minus b quantity squared, it's just a squared minus 2ab plus b squared. So that's where I'm getting this from. Okay. Combining all that together, we know that, and I'm going to erase some of this. We know that 5 times square root of x quantity squared is just 5 squared minus square root of x squared, which gives us the 25 here, the absolute value of x there. That simplifies to just x, because we know x has to be greater than 0 in these problems. 2 times the a, which is this, b, which is that. And so we multiply that together, and then of course 3 squared is just 9. And so this ends up being our answer there. All right, so we're going to move on, and this will be the last set of examples for this particular video. We want to write each product as a single radical expression. And so what this calls for us to do is to take the two factors that we have that have different indices, write them in exponential form so that we can combine the exponents by using the exponential rules, and then taking that and then changing it back into radical form. So for our first example, we see that the indices are different. This is a cube root, whereas this is an understood square root here. Indices are different, but the radicands are the same. So we could take both of these and change it into its fractional exponent equivalent. And so cube root of 3 is just 3 raised to the 1/3, and square root of 3 is just 3 raised to the 1/2. Since the bases are the same, we're using the exponential rule here, that if we have two exponential expressions and the bases are the same and we're multiplying, we can add the exponents. Okay, realizing that we can add the exponents here, in other words, we could rewrite this as 3 raised to the 1/3 plus 1/2, like that. But we know that we're going to have to find a common denominator. So What I did here in this example is anticipated that and just changed 1/3 to 2/6 and 1/2 to 3/6. Okay, so that's where all that comes from. So from here, once we do that, of course, if we add 2/6 and 3/6, we would get 5/6. And so from here, we know that 3 raised to the 5/6 using the rule here, we see that our m is 5, our n is 6. So we would take 5 here, write it there, 6 that's there, right as the index, and of course 3 raised to the 5th power is just 243. So this would be the simplest term, would be that particular product in simplest terms. All right, so for the next example here, we see that the radicands are the same, but the indices are different. So we're going to change this. And so we write this as 2 raised to the 1/3 times 2 raised to the 1/5. We know that we're going to have to find a common denominator. Common denominator between 3 and 5 is 15. So 1/3 is the same as 5/15. And 1/5 is the same as 3/15. So we'll take this, we'll add these together, add the exponents together, come up with 2 raised to the 8/15, and then from there we just rewrite. Okay, and of course we know that 2 raised to the 8 is just 256. So from there we have the 15th root of 256. Right, so for our next example here, we'll take cube root of 2, write it as 2 raised to the 1/3, 4th root of 3, 3 raised to the 1/4. Okay, and so for this one here, we see that the indices and the radicand are different. So really not much we can do with that one. So we would probably just have to leave it the way that it is there. Okay. However, one of the things that we do note here is that we could still change this to where our exponents could have the same denominator. And if we did that, then we would have a situation to where the indices would be the same. So we could put it back into radical form and then multiply them. Okay. So although it looks like we wouldn't be able to do anything with this, we actually could. So here we know that the least common denominator between 3 and 4 is 12. So here we know that 1/3 is the same as 4/12. And we know that 1/4 is the same as 3/12. So if we did this and we wrote both of these back into its radical form, that would be the 12th root of 2 raised to the 4 times the 12th root of 3 raised to the 3. And so now we can actually multiply all of these together. So we'll come over here and finish this up. So that would be the 12th root of 2 to the 4 times 3 to the 3. And of course, here that would be 12th root of 16 times 27. And 16 times 27 is 432. Okay. And so from that point, if we try to break this down anymore, we're going to see that there's not much we can do with that. We know that we have 4 factors of 2 and 3 factors of 3, and so we don't have a group of 12 of anything there. So no way that we could break this down, so this would be the simplest form that we would have there. Okay? So looking at our last example, example D, very similar to C here, we see that the indices and the radicands are different, and we put it into fractional exponent form, and looks like there's no hope, but if we take our exponents and write them as fractions that have the same denominator, then we can put it back into radical form like how we see here, and then multiply that way. Okay, and then from there we see that our answer here is 12th root of 648. And so with that, this concludes our video on adding, subtracting, and multiplying rational expressions. And so the next video will be about how do we actually deal with quotients of rational functions, powers, and the whole concept of rationalizing a denominator.